Hey there, APKL class. We're going to jump into the notes for section 4.4, and so we're continuing with our study of definite integration, and that's going to lead us into two of the most important theorems in calculus, first fundamental theorem of calculus and the second fundamental theorem of calculus. So today we're going to get into, or at least in this first part of the video, we're going to get into the first fundamental theorem, and we'll also get into there's a mean value theorem for integrals, and also average value, a definition of what that is pertaining to integrals. Okay, so let's take a look. First fundamental theorem of calculus, and this one, it's actually pretty easy to use, and all that it basically says is that so as long as f of x is continuous on the closed interval from a to b, and that capital F of x is the antiderivative of lowercase f of x on that integral, then if we take this definite integral, and so that's meaning that we find its antiderivative and call it capital F of x, and if we want to evaluate that from a to b, so we know what we've defined this as, it's the area under the function from a to b. And the first fundamental theorem gives us a method for calculating this definite integral, which is the same as finding the area under that curve. So we find its antiderivative, and then we evaluate f of b minus f of a, meaning in the antiderivative, we plug in our upper bound, we find that area, and we subtract out the lower bound. And that leaves us with just the area from a to b. Okay. So they give an example here. We can go through this real quickly. So guidelines for using this will be the first fundamental theorem. Provided you can find an antiderivative of f, you now have a way to evaluate a definite integral without having to use the limit of a sum, which we spent time on in the last unit, which was very tedious and not very fun. When applying the fundamental theorem of calculus, the following notation is convenient. So you take your antiderivative and you get your expression for that just using that power, most of the power rules that we've worked with. And then they use looks like a bracket. I usually just use a vertical line, and then that tells you I'm still going to evaluate it from a to b. And then after that, we just plug in f of b minus f of a. And so they do an example here. So if I were to find the antiderivative of x cubed, using my power rule, that's x to the fourth over 4. And then I do a vertical bar, or they use a bracket, from 1 to 3. And that shows, okay, now I'm going to evaluate and get just a numerical answer for this representing the value of that definite integral, which we know graphically means the area under the curve of this x cubed function. And so evaluating that, I'm going to plug the 3 in first. So 3 to the fourth over 4, that's right there, minus 1 to the fourth over 4. And so 81 fourths minus 1 fourth would be 80 over 4, or 20. And that's a simple example of using the first fundamental theorem of calculus. Now here, it's important to note it says it's not necessary to include that constant of integration where we were doing plus c at the end. Now those were called indefinite integrals because we didn't have a specific bound. We were just finding the general function that was the antiderivative of our original function, and in that case there could be some constant added to the end of that. However, here, because we are subtracting, we're subtracting some specific values in there, whatever that plus c was is going to get subtracted. It's the same antiderivative, even though we don't know what that plus c is, whatever it is, it's going to get subtracted, and therefore it's going to cancel out. So it's not necessary to include it. So we just have f of b minus f of a. Okay, so let's practice some of these. If you're doing this on your own, you could pause the video and work a couple of these out and just check them with the solutions as we go. But I'm going to keep moving through. So in example 1, we've just got a simple quadratic function. And so if we're using our power rule, we're going to have x cubed over 3 minus 3x. And I'm evaluating that from 1 to 2. And so as I simplify that, I would have 2 cubed over 3 minus 3 times 2, and then minus quantity 1 cubed over 3 minus 3 times 1. Okay, and then as I simplify that, that would be like 8 thirds minus 6. So 2 to the thirds, I get 8 thirds minus 6, and then I've got minus inside of here. This is just 1/3 minus 3. So 1/3 minus 3, which I would say 1/3 minus 9 thirds, I guess. So that would be like negative 8 thirds. 8 thirds. So there is some arithmetic to work around here. And then, like if I continue on here, this would be like, 8 thirds minus 18 thirds. Or I'm sorry, times 3, yeah, 8 thirds minus, or would that be, yeah, minus 18 thirds. Now, let me just do this here. I gotta jump up top here. So, right here, 8 thirds minus 18 thirds, which would be negative 10 thirds. Negative 10 thirds minus negative 8 thirds, which is going to be plus 8 thirds. And that's going to give me negative 2 thirds. I'm sorry that I kind of got a little bit all over the place there. You might want to leave yourself either write smaller, or you might have to do some scratch work off to the side on your arithmetic. But as far as the setup, hopefully you can follow that. So plugging in the 2 both spots, so I had to simplify that, and then plugging in the 1 here and simplifying that, turned out to be this part was negative 10 thirds, and I was minusing a negative 8 thirds, and turns out to be negative 2 thirds for that one. Okay. Part B, so I've got a 3. I would rewrite this probably as 3x to the 1/2 power, so that when you do the integral, it's a little easier to consider that. So when I do my antiderivative of that, it would be x to the 3/2 power divided by 3/2, which would be times 2 thirds. Now that 3 that's there times 2 thirds leaves me with a 2. So it's going to be 2x to the 3/2 power. Oops, 3. Oof. Get that looking a little better. 2x to the 3/2 power. And then I'm evaluating that from 1 to 4. And so that's going to be 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. And square root of 4 is 2. 2 to the 3rd is 8. Times 2 is 16. And 1 to any power is still 1. And so that's 2 times 1 is 2. So I should get 14 for that value. Okay. Antiderivative of secant squared. Well, we know that the derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. So I've got tangent of x, evaluating that from 0 to pi over 4. And so I'm taking tangent of pi over 4 minus tangent of 0. And so pi over 4 being like 45 degrees, tangent of that would be 1. Tangent of 0 is 0, and that would simplify to just 1. Okay, so moving on to example 2. So it says evaluate the definite integral using definition of absolute value. So definition of absolute value, I know that you've graphed these before, but sometimes we forget what it means. So, basically you're graphing a line. You're graphing the line 2x minus 1, right? But we know that because it has absolute values on it, that graph can't dip down below the x-axis. It can't become negative. So in other words, if I were graphing this line, I'd have a y-intercept of negative 1. I go up 2 over 1. And so that means it's going to cross, its x-intercept is kind of important here. So if I was thinking of the x-intercept, that would be a positive 1/2, because that's the point at which, this line, which if I didn't have absolute values, would just keep going down like this, right? It would just keep going like this. But because of those absolute values, when it hits the x-axis, it reflects back up. In other words, you do the opposite sign then of the stuff that's in here. It's like negative 2x, slope of negative 2, and a y-intercept of positive 1. That's the way it switches. So here's how you would evaluate a definite integral. And we could find areas of these triangles. I kind of sketched that out, and that's the way we did this in the past. But now that we're working on, using definite integration, what we could do is say, okay, well, I'm looking from 0 to 2. So from 0 to 1/2, which is where, it would start becoming negative, that's its x-intercept, it's this line. It's actually the line that has, a slope of negative 2 and a y-intercept of positive 1. You just switch those. So I would go like this. I go, okay, from 0 to that x-intercept of 1/2, I'm actually evaluating the opposite of 2x minus 1. Okay, and then I'll put dx on that. And then plus from then 1/2 to 2, now I'm just doing the 2x minus 1. Okay, so that's what they mean by the definition of an absolute value. That's, where the part where it would be negative, but it gets reflected, it means it's the opposite of what you have here. Okay, so if I were doing my antiderivatives, I would have, so I would have x squared minus x, I'd have my negative out here, and that would be evaluated from 0 to 1/2, and then plus, on this second one, I would have x squared minus 1/2 again, but not the opposite of that, or not 1/2, minus x, sorry, minus x, and then that's evaluated from 1/2 to 2, okay? So on this one, from 0 to 1/2, so I'd be putting in 1/2 squared minus 1/2, and then if I'm plugging in that 0, it's going to be basically minus 0 after that, right? So this is going to be 1/4 minus 1/2, which is negative 1/4, right? Like this is 1/4, because 1/2 squared is 1/4 minus 1/2 would be negative 1/4. But I'm doing the opposite of that, so that's just going to be 1/4 for that part. Okay, and then over here, I'm going to have, so on this part, this is going to be 2 squared minus 2, and then minus quantity 1/2 squared, and then minus 1/2, which we did before over there. So if you can stick with me here, this is going to be 4 minus 2, which is 2, and then minus 1/4 minus 1/2, which is minus negative 1/4. And so then I've got 2 plus 1/4, which is going to be 2 1/4. So when I add those together, I actually get like 2 1/2, or 5/2 for the value of that definite integral. So there is a bit of, arithmetic, and you got to kind of pay attention when you're subtracting. Make sure you put parentheses, around it, because especially if there's more than one term there, because you're gonna have to simplify what's in there, and make sure you subtract the whole quantity when you're done. If you're minusing a negative, that changes to plus. Okay. All right, so that was that one. All right, next one, we have we've got a parabola, 2x squared minus 3x plus 2, and it says, so use the fundamental theorem of calculus, find the area bounded by the graph of this parabola, the x-axis and the vertical lines x equals 0 and x equals 2. So in other words, that's telling us that we're going from 0 to 2, and we're going to find the integral of this dx. Okay. Now, I sketched out what this graph looks like, and I just graphed this on my calculator, but so the vertex is kind of at a weird spot. If you go negative b over 2a, it's like 3/4 is the x-coordinate, and then you plug that back in, you get like 7/8. So it's, I kind of approximated where that is. So it's 3/4, 7/8 for the vertex. Has a y-intercept of 2, so I mean, you can get, I tried to sketch that in there the best I could. But then we're looking at this, this red kind of colored in area under there. Okay, so that's kind of what we're calculating for the area, is that space that I colored in red. Okay, but now we're going to use fundamental theorem, so we're just going to use our, our formula, our power formula for calculating that antiderivative. And so I add 1 to the power here, so that's x cubed, and I divide that by 3, it'd be 2/3 x to the third, 2/3 x to the third, and then minus, and then this is going to be 3x squared divided by 2, so that'd be 3/2 x squared, and this is going to be plus 2x, and then we're evaluating that from 0 to 2. It's kind of nice when you have a 0, because then when you subtract, it just all becomes nothing. So we have to basically plug the 2 into each of these spots to calculate this out. And so when we plug that 2, we have 2/3 times 2 cubed, 2/3 times 2 cubed, minus 3/2 times 2 squared, plus 2 times 2. And then, like I said, we're going to subtract, plugging a 0 in, which is basically subtracting 0, so that doesn't change anything. When we simplify this one, we end up with like, we got here 16 thirds, because 2 cubed is 8, and times 2 thirds, 16 thirds, and then minus, what's this one going to be here? So we'll have 4/12 divided by 2 minus 6, and then plus 4. So that's going to give us, let's see here, so if we go 16 thirds minus 16 thirds minus, let's be 18 thirds plus 12 thirds, we get common denominators. So that's negative 2 thirds, and then plus 12 would be positive 10 thirds, or 3 1/3 it looks like. Okay, so that's what we get for evaluating that one. I do want to show you real quick on your graphing calculator. It's real handy to be able to check some of these, and I'll show you how you can do that a couple different ways. So I entered this one into the calculator we have on your Calculator Pro, and I just check the vertex that, and let's see, well, I didn't quite get the vertex by touching it there, but you can do that the same way. You can go second, calculate, and if you want to do your vertex minimum, I hit 3 for minimum, and then you just have to do a left bound, hit enter, a right bound, hit enter, and then it tells me my vertex 0.75 and 0.875. Anyways, so if we're going to evaluate the antiderivative, that area, you can do that from the graph screen or from the home screen. I'm going to show you that. So if I hit second and then calculate again, or second trace that calculate, option number 7, you can hit that, you can hit 7, and then it asks for a lower limit. Lower limit is the 0 that we had, so I'm just going to type in 0, I'm going to hit enter, and then it's asking for an upper limit now, and that was 2, so I hit 2, enter, and it actually shades in that area in question, and it tells us. Now sometimes there is sometimes residual error when it calculates, especially on the graphing screen, but 3.33, it starts to repeat, but then it's, kind of gets off a little bit, but 3.33 repeating is, that's 10 thirds, and that's what it's showing right there. It's actually demonstrating, the area that I had shown here when I sketched it. Okay, so I also want to show you one more real quick from the home screen. So if I hit second quit, and we just want to do this real quick from the home screen. Now I had this entered in already in Y1, so I'm just going to use it from there instead of retyping. You could retype it from the home screen, but I'm going to use that shortcut button to do that. But what we can do is we can hit math, so the math button right under the alpha button right there, and then item 9, that's integrate there, so if you hit 9, and then you can hit your bound 0, and then 2 up there, and then for my function, I'm gonna since I've already got it in y equals alpha, and then F4 is that shortcut button, and I'm gonna y1, I've got it in there, and it's already got my variable of integration as dx, and hit enter there, and then it gives me the 3.33 repeating. Okay, so that's another way you can check your definite integrals with your calculator. All right. So let's see. Okay, last thing I'm going to get through on this video, I do want to talk about mean value theorem for integrals, and then just what average value means. Okay, so here it says, so if we have a continuous function on a closed interval, it says there exists, so this is an existence theorem, there exists a c in that closed interval, so somewhere between, in this case 1 and 2 in the example I have, but between a and b in general, such that the area, so the integral or the area under that function, is equal to f of c times b minus a. Now what does that mean? F of c, like we kind of did this a lot when we were first discussing like Riemann sums, but this is your height, okay? The f of is the height of that, and then the b minus a, that's the width, right? So height, and because width, b minus a, 2 minus 1, that would be our width, and the height is, or f of c is the height. What they mean by c is, okay, so typically these, we got a curved function, it's a quadratic, right? What they're saying is this kind of odd-shaped area, there's some c somewhere in the middle here that when I square this off and make it like just a rectangle, that area is going to match the area of this yellow space. It's kind of weird shaped like that. So that's what they're doing here. They're saying this yellow area and this yellow area are the same amount. And there's a point, a height, that makes that true. And in this case, it's 7/3. We'll get to how you find that, but there's a way that we can find that. We can find, hey, the height, the average. So what they're really saying is the average height of this parabola, the average function value, is 7/3, and that occurs somewhere between 1 and 2, and we can find that value as well, and they're calling that c. Okay, so there's some c value, in this case between 1 and 2, that tells me the average height here. That's gonna, so I'll have the same area, here is what I do right here. So I should be able to make a rectangle out of that and find, find that c value, that x coordinate, and that y coordinate where that would be true. So that's what this is saying. So we can find, so again, integral is an area. This is height, this is width. I'm multiplying width times height. Okay, now this is important, mean value theorem, but then what they ask you more often for is for the average value. And so finding the average value means finding the height, okay, the average height. That's what it really means. It's like, what is this, finding that 7/3. And now, if we want to solve this equation for height, which is f of c, what do we have to do? We have to divide the area by the width. So if area, I'm saying this is area, is height times width, then to get the height, the average height, I have to divide by the width, divide by the b minus a. And that's what's happening right here. 1 over b minus a, we're dividing it. Okay, and that's going to give us, and then we're multiplying, we're actually taking, this is our area, and it's going to get divided by the b minus a, and that leaves us with the height. Okay, think about algebraically what you do here. You would divide by b minus a on both sides, and that's going to give you the f of c. Okay, so they're giving us a formula to find that. All right, so I want to just run through this. So the average value, find that average value. So this is our parabola right here. Okay, so from 1 to 4, so from 1, 2, 3, 4 to 4 right in here. Okay, so I want to figure out what is the average height somewhere, wherever that is in here. Right, that's going to rectangle out and make that area the same. I'm going to erase what I just wrote there. But okay, so the way that we do that is we go 1 over b minus a, which is really dividing by the width. So that's 1. So b minus a is going to be 3, right? 4 minus 1. So I've got 1/3. I take that times the integral from 1 to 4. And this is calculating the area now, the actual area of 3x squared minus 2x dx. Okay, and so I just need to do my antiderivative. I want to calculate out what that is. Okay, so when I do my antiderivative, this is just going to be x cubed minus x squared. I'm going to evaluate that from 1 to 4, and I'm going to multiply it by 1/3 when I'm done, right? Times 1/3. Okay, so 4 cubed minus 4 squared, and then minus 1 cubed minus 1 squared. It's going to end up being minus 0 on that. And so I've got 64 minus 16, and then minus 0 there. So that's, I got 1/3 right there. 1/3 is 64 minus 16, which is 48, and this is minus 0. So I got 1/3 of 48, which comes out to 16. So my average height on this parabola is actually 16. You can see it goes up to, like, I gotta scale up to 50 there, but the average height is 16 in that interval. Okay, in this interval from 1 to 4, my average height is 16. Okay, and then it says find the value of c guaranteed by the mean value theorem. Well, all we have to do there is take our original function and then just set it equal to 16 and find where does that x coordinate lie. So we just take our 3x squared minus 2x, set it equal to 16, and solve. What I would probably do in this case is, well, I don't know if it factors. It might factor in this interval. Let's see if it factors. We could just stick it in our calculator too, but minus 16 equals 0. So I'd have to go 3x, and if I go 8 and 2, yeah, that works. 8 and 2, and I would have to go minus and plus, yeah, and so I get x equals 8 thirds, negative 2. Now negative 2 is actually not in the interval we're talking about, so it's just x equals 8 thirds. Okay, and that's how we would solve. So once you get, once you get that average height, and then to actually find that, you got to get that first, the average value first, and then you set your function equal to that to see where that x-coordinate is. And they actually have that on here. 2.67 is approximately that 8 thirds, and then 16. Okay, so that is it for the first part of these notes. We'll finish up the rest of them. Maybe 1 or 2 more videos. We'll see how long that takes.